Intro Algebra Lesson 4-8A. We're getting better with our graphs now. We're able to use our graphs to actually solve some equations. We have slope-intercept form, and we can use input-output tables. We can also find x and y intercepts. We're getting pretty good with all the things that involve graphs. So today I want to look at something that is called a relation. This can be a little tricky at first. It might take some time to get good at it. A relation is a situation where an input can have more than one output. Now this sounds very strange. An input could have more than one output. It's any set. Set is just a fancy way of saying a group of ordered pairs. When you make an input-output table, you're making a group or a set of ordered pairs. We're talking about a relation that is any group of ordered pairs. Not every single group is going to be called a relation. I mean, we can call them a relation, but some of them we have special names for. But they can all be considered relations. All right? So what this is saying up here is that I can plug in a number, do math, and get an output. Plug in a number, do the math, get a different output. Plug in a number, do the math, get yet a different output. That would still be considered a relation. All right? We have something that's known as a vertical line test. And the vertical line test allows us to determine whether we're dealing with a relation, which is any group of input-outputs, or if we're dealing with a function, which is not a relation necessarily. It fits the description of a relation, but not all relations are functions, because if it's truly a function, then the input has to have exactly one output. And a relation, it's okay to have more than one output, so they're a little bit different. So here's how the vertical line test works. You need something that you can hold vertically. You could use your finger, you could use a pencil, you could use a ruler. I've got right here a meter stick. All of these work as vertical line tests. You need to be able to make a vertical line. Not a horizontal line, but a vertical line. You take a graph, and you look at the graph, and you hold your vertical line. Now, if the vertical line ever touches the graph, not the x or y axes, you're not worried about the axes, but if your vertical line ever touches more than one point of the graph itself, then it is not a function. It would be considered a relation. So right here, the graph is good, because I'm only touching the green area in one spot, so it's okay. But as soon as I move a little further over, bzzz, it's touching more than one spot at a time. So it's good, 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 bzzz, good, 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 bzzz. So this would be considered a relation because it touches more than one spot at a time. The green S looking shape touches more than one part of the vertical line at a time, and that is not a function. It has to pass in order to be a function. So we look at the next one. Now, if I start here, the blue line, it only touches one. Good, 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 good. It never touches more than one part of the blue, so we would call this a function. Yes, it's still a relation. It's just a special relation known as a function. All right, looking at this graph, it might start off okay, but right here, bzzz, it's touching more than one part of the graph, so that is considered not a function, so we'd call it a relation. And lastly, you might recognize that line, because this is the kind of stuff we've been graphing lately. That's linear. And as we look at that, it passes. It only touches one part of the red the entire time. So that would be considered a function. So the graphs that we've been making lately have been either horizontal, which that's going to pass the vertical line test, diagonal of some sort, which that passes the vertical line test, or a vertical line, which is not going to pass the vertical line test because the vertical line would buzz on all of them. So undefined slopes, which are x equals, are not functions. They would be considered relations. So function notation. This sounds very crazy. It sounds complex. It's actually very easy. This is pronounced, it's where you see an F and then an X inside parentheses. It does not mean F times X. You pronounce that F of X. F is a rule that's being applied to X. Now that sounds a little crazy. Rules don't have to be hard. My rule could be that whatever X is, I'm going to add 7. So then F stands for the idea of add 7. Take X and add 7. And somebody could say, well, what if X was 2? Okay, add 7 and I get 9. But what if X was -1? Okay, add 7 and I get 6. It doesn't matter what it is. If f for my rule stands for adding 7, I can make an input-output table and come up with all kinds of outputs according to those inputs by simply applying the rule to the number that I put in for x. Whatever number I put in, I'm going to add 7 to it, or whatever my rule might be. F of x is the same as y. If you see y equals mx plus b, it's no different than f of x equals mx plus b. You do not ever try to solve for f or separate f from x. It's not like it's dividing by anything. It's just like the value of y. These two are exactly the same. Example number 1. The question is, are we dealing with a function? And if so, we need to state the domain and the range. If you recall, the domain is the inputs, and the range is the output. Typically, input involves the x, and output usually involves the y. If you look back at our example right here, we would stick numbers in for x, do the math, and out pops y. So input is x, output is y. So we're trying to decide, if we have this type of an input and an output, would we be dealing with a function or not? Well, let's take a look at the data. 4 goes in and becomes a 0. Next 4 goes in and becomes a 1. Then 6 goes in and becomes a 4. And 8 becomes a 4. Now we said a moment ago when we talked about relations that it can't have, if it's a relation it can go in and get different outputs, but in order to be a function, every time a number goes in it must produce exactly one output. And if you look here, this one's producing one output, this one's producing one output. Yeah, it's the same, but that doesn't matter, but the 4 is the problem. 4 goes in and comes out 0. Later 4 goes in and comes out 1. Can't do that if it's a function. And we can also check it on the graph. If we make a graph of the data, let's go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Just so we have it spread out. If you graph these coordinates 4, 0, there's 4, 0, and 4, 1, and then you graph 6, 4, and you graph 8, 4, you will notice that it does not pass the vertical line test. Because right here, bzz, it touches 2 of the dots at the same time. Bzz, those are good, bzz, good, bzz. It can never touch 2 points of the graph at the same time. And that only would happen is if the same number goes in but produces different outputs. It doesn't matter if different numbers produce the same output. That's fine. That's these 2 dots over here that are okay. But if you have the same number going in producing different outputs, it's going to create a vertical line which won't pass the vertical line test. So we would call this not a function, this is a relation. Alright, let's look at the next one. Now 1 goes in and it's a 2. Good. 3 goes in and it's a 4. Good. 5 goes in and it's a 4. That's okay. 7 goes in and it's a 6. It never has the input going to 2 different spots like up here. It might have 2 different numbers going to the same spot, but that's okay. It's just the same number going to 2 different spots that's not okay. So we're supposed to state the domain. So the domain is all the inputs, 1, 3, 5, 7. And the range, all the outputs, 2, 4, 6. We only do that if it's a function, which this is. So because it's a function, we can state the domain and the range. Alright? Lastly, let's evaluate this. This may seem tricky. It's actually pretty easy as well. There are 3 different values of x, so we're going to plug them in 3 different times. So we would say f of 4 means take the rule and apply it to 4. Now the rule is 7 minus 3 times whatever x is. So 7 times 3 times 4 means 7 minus 12, which is going to give us negative 5. So we can say f of 4 is equal to negative 5. When the rule is applied to 4, we get negative 5. Don't try to divide by 4 and solve for f. We're not solving for f. Okay, next the rule is applied to 0. So it's the same rule. 7 minus 3 times 0. 7 minus 0 So when we apply the rule to 0, we get 7. So that's what we would get. We apply the rule to 4, we get -5. We apply the rule to 0, we get 7. We plug a number in, we get a number out. We plug a number in, we get a number out. And lastly, we can apply the rule to -3. So 7 minus 3 times the -3 means that we're going to get 7 minus -9. So we got to watch our signs. That's plus positive. So we end up with 7 plus 9 is 16. When we apply the rule to -3, we get positive 16 because that's plus positive. So that's how you would apply the rule to different inputs. Alright? One more. We would apply the rule to -2. 10 times -2 plus 3. 10 times -2 is -20 plus 3. That equals -17. So when we apply the rule to -2, we get -17. Again, we're not solving for f. F says there's a rule being applied to the number, and then you get an output.